Welcome to solverfy.
So we have a cylindrical rod of length L, R0. We want to find the field. So let's find the field for an R that is greater than R0, that is any point outside the cylinder. So for that, we will use a Gaussian surface that looks something like this. It's another cylinder enclosing our cylinder. Why do we use this? The reason is because our system is cylindrically symmetric, we expect the electric field to be radially outwards and depend only on the distance from the cylinder. That is, we don't expect it to depend on where it is around the cylinder. So on such a Gaussian surface, on these two surfaces, the two circular surfaces on two ends, the electric field would be vertical to the Gaussian surfaces, and there would be no contribution to the flux. Whereas the the center surface, the electric field will be perpendicular to the area, and hence we can find the electric field very easily. Now, let's say the radius of the cylinder is r. As we've seen already, the flux on the two side surfaces will be 0. So the total flux will be only due to center surface. Let's say this Gaussian surface has an x length, and we know that the radius is r. The radius of this circular surface, of this cylindrical surface, would be x times the circumference of the circle, which would be 2 pi r. This will be the area. We need to multiply it with the electric field. And we expect the electric field to be the same all over this cylinder because of our cylindrical symmetry. We know that this is equal to charge enclosed divided by epsilon naught. So if we extend this cylindrical surface all over our Gaussian surface all over the cylinder, and we ignore the fringing effect, and we put x is equal to L, we will see that E into 2 pi r L is equal to Q by epsilon naught. Now, the charge enclosed is simply the charge density times the volume enclosed. And you know that the volume enclosed will be the volume of the rod that is enclosed. That will be the area of the rod, that is pi r naught squared, times the distance L. So that will be rho times pi r naught squared L naught. So cancelling a few common terms, we see that the electric field is rho r naught squared by 2 epsilon naught r, and it's directed radially outwards. Now for part B, we consider r is less than r naught. Then we use the same Gaussian surface, and we have the flux is equal to E into L into 2 pi r, but this is equal to charge enclosed divided by epsilon naught. And in this case, the charge enclosed will be, let's say this is our cylinder with radius r naught. Let's say we are considering a distance r. So we consider another cylinder with this radius. So the charge enclosed will be rho times pi r squared L. So that is rho pi r square L by epsilon naught. Now cancelling the common terms, you can see that r is also gets cancelled, giving us E is equal to rho, I'm sorry, this is an r squared, so rho r by 2 epsilon naught. Again, this field is also directed radially outwards.